a one-step equation, one operation is performed to x, and therefore one inverse operation is used when solving the equation. In a two-step equation, two operations are performed to x, and two inverse operations are needed to solve. These inverse operations need to be performed in the reverse order of operations. The reverse order of operations typically means that when we're solving a two-step equation, first we add or subtract, and then we multiply or divide. Let's look at this first example. In this first example, 8x minus 7 equals 33. We can use our normal order of operations, PEMDAS, to understand what's happening to x. First, we multiply x by 8, and then we subtract 7 in order to get 33. Now, when we're working backwards to solve, that's when we need to think about the reverse order of operations. The first thing that we need to undo is the subtraction by 7, and then we undo the multiplication by 8. That means, as typically is the case, our first inverse operation involves addition or subtraction. We want to first undo subtraction by 7. That means my first inverse operation is to add 7 to both sides of my equation. 8x minus 7 plus 7 just leaves me with 8x on the left-hand side of my equation. 33 plus 7 is 40. Now I only have one operation being performed to x, multiplication by 8. I undo that with the inverse operation of division. I divide both sides of my equation by 8. 8x divided by 8 leaves me with x. And then x equals 40 divided by 8, 5. 5 is my solution to this equation. If I want to check my work, I can go ahead and plug it back in. I can plug 5 in for x and check to see, does 8 times 5 minus 7 equal 33? 8 times 5 is 40. Does 40 minus 7 equal 33? Yep, 40 minus 7 is 33. 33 equals 33 is a true statement, and so I have verified that x equals 5 is my solution to this first example. In the second example, using my normal understanding of order of operations, what's happening to r is that I'm dividing r by 6 and then adding 1 in order to get 8. When I solve, I need to work backwards. So first I undo that addition by 1, and then I undo the division by 6. The inverse operation of plus 1 is just minus 1, and I need to perform that inverse operation to both sides of my equation to maintain the equality. R divided by 6 plus 1 minus 1 just leaves me with R divided by 6. R divided by 6 equals 8 minus 1, which is 7. Only one thing is happening now to R in this equation, R divided by 6. I need to undo that division with multiplication, multiplying both sides of my equation by 6. R divided by 6 times 6 leaves me with R. R is isolated. R equals 7 times 6, which is 42. 42 is the solution to my equation. I'm going to go ahead and check that by plugging r equal to 42 into my original equation. Does 42 divided by 6 plus 1 equal 8? Does 7 plus 1 equal 8? Yes, it does. 7 plus 1 is 8. 8 equals 8 is a true statement, and therefore I have checked my solution. Now I want to briefly review work that is not accepted. So there's a trick that is sometimes taught to students that you can move, let's use a different color, that you can move a term to the other side of the equal sign just by changing it from positive to negative or negative to positive. So a typical trick would be to move this minus 7 over to the other side and say 8x equals 33 plus 7. Now this is considered a trick and not a justification, and this work is not accepted in algebra. Instead, we need to show plus 7 to both sides of our equation and not just perform this trick. Similarly, you are not allowed to move that plus 1 to the other side and say r divided by 6 equals 8 minus 1. If this is a habit that you're in, I need you to break it right now so that you're not really frustrated with your grade in Algebra 1. So get out of this habit of just using the trick of moving a term from one side to the other flipping it from negative to positive or positive to negative, and get in the habit of solving using inverse operations, which fully justifies your answer.